we go. Okay, so this is going to be integration for physics. This is the I word I was referencing earlier. Now, you're going to get a lot of this stuff in a much deeper detail when you're in your math class. Okay, and you get to learn you get to do all the Riemann sums and all that cool stuff, and it's going to be awesome, and you'll love it. It will touch the very heart of you when you take it in class. We're not going to mess with that in here because, frankly, I don't remember how to do it. So, but neither will you once you finish your AP test. You won't remember how to do it either. Okay, so we are going to start with, of course, a graph, and we're going to start with the same graph that we had in the previous lecture, where I walk at 5 meters per second. I'm sorry, at 2 meters per second for 5 seconds. Right? Yeah? Okay. And there's the boxes, and we know that one box represents 1 meter per second by 1 second, and that area isn't meters squared. It's 1 meter per second times a second, which is a meter. That area is not a classical area unit in the sense where it would be meters squared or centimeters squared or something like that. It graphically represents the units of 1 meter for a displacement. Okay, we already have an equation for relating our velocity and our displacement. Okay, it was equation number 2 from our equation list. Okay, delta x equals v naught plus v over 2 times t. Okay, remember that the acceleration has to be constant for this to work. Acceleration has to be constant for this to work. In this particular case, it is 0. All right, so we get 2 meters per second plus 2 meters per second divided by 2 times 5 seconds. Our v naught is 2 meters per second. We start at 2 meters per second. We finish at 2 meters per second. So our average velocity would be 2 meters per second. And our time is 5 seconds. And so we multiply it out. We get 10 meters. Or we do it the other way, where delta x equals v naught t plus 1/2 at, which was equation 3. Acceleration in this case equals 0 again, and because it equals 0, we can cancel out the 1/2 at. And we're back left with x equals v naught t. So it equals 2 meters per second times our 5 seconds, which equals 10 meters. Funny how that answer hasn't changed yet. All right, so we're going to take that part right there, okay, and move on. Now, warning. A profound idea approaches. It is this: graphing quantities that multiply to give an area, right? Crap, when I wrote this, it totally made sense, but now it doesn't make sense. Graphing quantities that multiply, that gives an area, and that area on the curve equals the product of the quantities that you're multiplying. That's the profound idea. That multiplication multiplication gives a product. Thank you. It gives a product. It also in analytic geometry implies an area, and that is the truly profound idea here, because okay, if we create another graph here, Okay, and we do something similar to our qualitative graph from last time, except this time we have a V naught. Well, I'll let you guys see this. Okay, we have a trapezoid like we had before. And there's our area. We shade in the area. And V naught is down here. It's 2 meters per second. And our final V is up here at 6 meters per second. Yeah? Okay, and there's another way we can find the area of this. And we can cut this up into two different areas. We have area 1, which we will call delta x1, which would be our displacement. This would be our displacement based solely on the idea that we started traveling at 2 meters per second at the start of our time. You see that? Yep. This is the displacement we get from having an initial velocity. Is that right there? The triangle that is above it is delta x2. This is the displacement we get for having an acceleration. We are going to accelerate and our velocity is increasing. So this is the displacement from the increase of the velocity, and this is the displacement for the initial velocity. We cool? Okay. So, delta x equals v naught t from before, right? Or delta x1 equals v naught t, which is, our time, which is these 5 seconds, times our initial velocity, which are these 2 seconds. All right. As Granddaddy rears her ugly head. Her lovely, beautiful head. Sorry, it's a figure of speech. Okay. Okay, so the rectangle is going to have an area. The rectangle is going to have an area of 2 meters per second times 5 seconds, which gives us 10 meters again. But now we have x2, and this is a little different. This is going to have the area of a triangle, which is 1/2 the time. Okay, so it's 1/2 the height times the base, right? Which the base is going to be v minus v naught, because this is v. So we're looking for this distance here, right? Which is going to be v minus v naught, and we plug that stuff in, and we'll get 1/2 times 5 seconds times the quantity 6 minus 2, which is going to wind up being 4. And that, once again, 10 meters. Really, that's not going to be a running joke for us, but it just happens that 10 meters is our answer again. Okay. Mind you, this works because that blue, this teal line up here is a straight line. Okay, this makes the possibility of solving this in an algebraic way much, much easier. Okay, where v equals at plus v naught, we have an equation for that. Let's say we want to plug it in there. We are going to substitute that v into that equation. And so we'll get that, yeah? That make sense? All right, so we get the at plus v naught, we plug in there, and we wind up putting that. Well, the v naught and the v naught are going to cancel each other, leaving us with 1/2 at squared. Look familiar? It should. Because when we find the total area of everything underneath our trapezoid down here, if we add this total area, that's going to be x1 plus x2. Okay? Finding the sum of the areas is an important concept for the future of this lecture. Okay, we know that we can add these areas together to find the total area underneath the graph. Yes? Profound idea. Okay, so we add these two areas together. We're getting 1/2 AT squared plus V naught T. This should look familiar to you guys. This is equation 3 from earlier. So, this process of determining a quantity by finding the area under a graph is called, everybody all together? Integration. Good. I knew you could do that. Okay. So that's what we're going to be studying now, except we're going to turn it up a notch. Because now, what is the difference in our curve? It's curvy. It is actually a curve. It is not a straight line anymore, and this is where the difficulty comes. And this is where I start getting, frustrated. Because if we're going to find another area, okay, I can take, let's say we want to go from 0 to 3 seconds, right? We want to find how far we travel in the 0 to 3 seconds when we're traveling like this. Well, if we do it the way we've been talking about it before, we can divide it up into sections. Okay, but I'm sick of trapezoids. I don't want to do trapezoids and triangles anymore. Those are a pain. I just want to do rectangles. Rectangles are easy. It's one thing times another thing. We don't have to deal with fractions. We don't have to add. I just want to do rectangles. So, we divide our space up into rectangles. And we can, we just, those 3 rectangles, and we create a rectangle here, and a rectangle there, and a rectangle there, and I can add them up and come up with an approximation. Okay? But how good of an approximation is this? It's terrible. It's a horrible approximation because we can't... Oh, that's not what I wanted. Because this area right here and that area right there, okay, are, and that little section right there, okay, they're not getting counted. Okay, let's blow this up to something larger, and that's a whole lot of area that's not getting counted with our rectangles. So, okay, well, I'll stick with the rectangles, but I'm going to make them smaller. So I'm going to make narrower rectangles to maybe fill up more of this approximation. So, all right, so we have too much missing area, and let's break up this into more sections. All right, so I draw green rectangles in there. And I make more of them. So you've got one there, and one there, and one there. Okay. Now this is getting a little better. So let's make some rectangles here. All right, and those look a little better. All right, because we're going to have a little section here and a little section there. So we're taking up more. We're taking up more area, right? But are we there yet? No, we still have these little bits. We want to get as close as we possibly can. Okay, and we fill all that in with area, and we add all that area up. Okay. And we find that the smaller areas that we're adding together, the less error we're going to get in our approximation. Okay, so we keep making our rectangles smaller forever. Okay, in all practicality, this is impossible to do. Forever is a really long time. Okay, to quote Prince. It's the beginning of Let's Go Crazy. Look it up because it's a great song. Okay, so we keep doing this forever. Luckily, we have math and we have the intelligence to foresee that if we do this forever, we're actually going to start dividing these up into teeny and teenier delta t's. Right? Because remember, the width of these rectangles are change in time, right? Okay, so in this little change in time, this little delta t is going to keep getting smaller and smaller. Oh, well, hold on. I totally went too fast through that, so let's scroll back. Okay, so we're going to do the area of any one particular, to give you a little preview of what's going on here. The area of any one particular one of these rectangles is the velocity of that rectangle, I'm sorry, the height of the rectangle, which is our velocity, right? This is our VT graph. Guys? Okay, times the width of the rectangle. And that's going to give us our VI delta T. Okay, now, the approximation is adding them all together, right? So, we are going to sum them. Okay, and if we sum them all, okay, if we call this velocity VI, any particular one of these, we'll call it I. And if we sum all of them, then our notation becomes sum from I equals 1. So this first one, this guy right here is V1. Okay, and here's V2 and V3 and V4, and so on. To however many we're going to have, if this is our nth rectangle over here, if we add them all together, now we're getting a general term for our approximation. Yeah? You guys with me here? Gabe, you good? You hanging with? Okay. Now this is our total area. So, here comes the fun part. Let's take the limit of this as our delta T approaches 0. Because that's really what we're doing if we're making our rectangles forever, right? We are making our delta T, if we keep cutting them forever, we're making our delta T go to 0. So we throw that thing back in there, and this, okay, so mind you, how many rectangles? How many rectangles will we have if delta T goes to 0? An infinite amount. Again, forever is a really long time. We're not going to do this. We're not actually going to draw each one of them, but we have the mathematical tools to calculate what happens when we do have an infinite number of them. Okay, there's an infinite number of them. So when we do an infinite number, okay, we're going to look at an infinitesimal slice. That one little thing right there is one little teeny tiny slice, just one of them. What do we have? That height right there is V or VI, or V of T. Okay, at that moment T, right? At that particular time, that height is V of T. And because it is infinitesimally small, the width of the slice is dt. And this is where we make our transition from delta t to dt. Okay, dt means an infinitely small little portion in there. So, what is v of t dt? What does that represent? I'm hearing really rumbled. Okay. It represents the area, but what does the area of a VT rectangle represent? The displacement. And so if we have a dt right here, then this whole area, dt times v of t, is our infinitesimally small displacement. So what we are adding, all these little slices, are the itty-bitty little dx's. They're the itty-bitty little dx's, okay, of our displacement. That's what each slice represents. So, each dx equals v of t dt. Okay, now just off to the side, this should make some sense to you guys because velocity v of t equals, if you manipulate this a little bit, is dx dt, right? And so if you divide both sides by dt, you get vx equals dx dt. Yeah? Okay. So that should make some conceptual sense for you guys there. Okay. If we add all of these infinitely small slices together, infinitely thin slices together, we are going to get, okay, mind you, this is the coolest, one of the coolest functions, okay? If we add all of these, adding all of these means sum. And there's a cool mnemonic for this. Sum I forgot to put shoot. Sum, okay, or if we make that, let me put that right in there, and then is sum, which becomes the integral of dx if we sum all of the infinite slices equals that. Okay, so the sum of infinite slices gives us this guy right here. This is the integral symbol. This means the sum of infinite portions. Okay, the sum of infinite numbers of infinitely small portions. That's what this symbol means. Okay, and these are the portions. So if we add all of the itty bitty x dx's that we have, or itty bitty delta x's that we had in there, that's going to equal the sum of all of our itty bitty vt's times dt. Yeah? Okay, and so our displacement, our total displacement equals the integral of v of t dt. This is how we do it in physics. Okay, now, there are lots of rules for integration. You will find them in your appendix. I am not going to go over all of them because, once again, frankly, I don't remember all of them. I will be keeping up with you guys. I will be keeping up with you guys when you're doing your integrations. I don't remember them, okay? But there's only so many that we really have to deal with in this class. Okay, we'll have some sines, we'll have some cosines, we'll have some natural logs. But we don't get much more into it than that. Tonight's homework, you'll have some practice at it. Okay, so I'm not going to teach you those here. That's why you have math. We have other things we have to deal with. Okay, so that's why you're taking calc. However, we will go over one of them because this is the simplistic version of one. And it's called the power rule. If you remember the power rule for derivative, this is the backwards power rule. It's just going backwards. So remember that integration is backwards derivative. So we're going to take a basic function. V of t equals bt. I'm using b because it's not a. A can be confusing. Why? Because it might be acceleration. I'm not saying acceleration. I'm saying some constant. All right, b here is some constant. See, it's a constant. Okay, and we're going to raise that t to the nth power. So this is going to be bt to the n that we're going to take the integral of. Now we know that dx equals v of t dt. So we're going to substitute that v of t with the bt to the n. Now, as far as units are concerned, that dt, that infinitesimally small t, is still a time unit. It's still infinite number of zeros, 1 seconds. It's still a time unit. And so what we're getting here is still multiplying whatever this is times a time. All right? And so when we multiply t times t, we're going to get t squared. If we multiply tn times t, we get what? T to the n plus 1. T to the n plus 1. All right, now, so if we take the integral of this, I'm going to add a little bit to it. It should also be the integral of dx still equals that. Okay, so we integrate both sides, and bt to the n dt equals, well, it's going to equal bt to the n plus 1 because we're multiplying by that t, right? If we add them all together, and the total time is going to be your total t, right? If you add all of your dt's together, your total time is going to be your total time. It's going to be your t. However, for some reason, and again, this is, I don't remember why, it just is, and you're going to learn it in calc, so tell me then, you have to divide that by an n plus 1. Okay, but if you recall, if we were to take the derivative of this right here, this n plus 1 would multiply out in the front, and if we already have a 1 over n plus 1 there, this is going to be n plus 1 times n plus 1, which will return us to bt to the n, right? Okay, so this is how they are backwards of each other. The derivative of this is going to equal our original function. Okay, I don't want to hear about the plus c right now. Okay. So, if you open your book to A27, appendix page 27, you'll find your table of integrals. I'm not going to show you right now. You guys can do that, but that's where it is. You guys need to read that, particularly those of you that have not yet been introduced to the integral. You need to read it. You're going to be fine in here, but this integral part and some of the derivative part is where you guys are going to have some tough trudging for a while. Okay? I understand that. Don't stress. Just work hard. Okay? Have faith in the fact that you are going to understand it when you keep working at it, and you'll get practice at it. Okay? Trust me on this. Okay, particularly if you're not there yet. All right, so we've got all this stuff. We've got our sum equals sum. Delta x equals the integral of vt dt. Now, if we solve this, our delta x, we take what's called the definite integral in here because we know where our beginning and ending is. And we will have an initial time. We'll have an initial time and a final time. This would be our time initial. This would be our time final. And this is why we don't have to use c. So there. So our example. We're going to use the example that we actually drew way in the first slide. So we had this slide way over here. Oh, where'd it go? That one. We are going to use this formula. Okay, so we're actually going to integrate using this one here. Now, it's going to be pretty simple because it is a straight line, but you'll see where we're going with this. So, that equation winds up being 0.8 meters per second squared, because that is the slope of the velocity time graph, so we know that's an acceleration, so those are the units for it, times time, plus our 2 meters per second, which is where we started. This is our v naught. Yeah? Are we good there? Okay, this is v of t equals v naught equals vt plus v naught. All right. So we want to find what is delta x at t equals 5 seconds. Well, that's our given. That's our find. So we're going to solve. And to solve that, we're going to find the integral of dx. The integral of, or we know that delta x is going to equal the integral of v of t dt from 0 to 5. This is our vt. So we're going to plug this in here times dt, and we'll do this integration. So we throw that in there. All right, and when we integrate it, okay, this t, according to the power rule, okay, that's where my, okay, this t, according to the power rule, will become a t squared, because t to the first plus 1 is t to the second, and then we have to divide by that exponent again. Plus, well, there's essentially no t here, right? Okay, which means, or it's a 1. We can multiply by 1, and 1 equals t to the 0, so that becomes 2t. And we divide by this t to the 0 plus 1. We divide by the 1, because that's the new exponent, and nothing really changes there. But this becomes our function that is integrated. But we're not done. All right, that's how it works. Okay, so then we take this, and we need to evaluate it from 0 to 5. And that is all that that vertical line means. It's just saying that we are going from a starting point of 0 to a finishing point of 5. That is our range of t that we are doing integration from over. And the way this works is it's a final minus initial situation again, because delta x is final minus initial. So it's what our final was. And why isn't that a minus? Shoot. That should be a minus. No, I totally screwed that up. I screwed that up. Okay, so that's the first term, is the 0.4 times 5 squared plus 2 meters per second times 5 seconds. That's the final. And then minus the initial, but because initial is at 0 seconds, the 0 plugs into the t squared and the t and makes them go to 0. So we have a 0 there, and that creates 20 meters. This winds up being 10 meters. Again, that's still 10 meters. We get 10 plus 10 equals 20 meters, and that is our delta x. And that's the end. So, you guys, your homework tonight